Looks like it did. Welcome to the Monday seminar. Really excited to see everyone, and very happy that Federico Ciardo has joined us from Northwestern, where he recently started a faculty position. You saw the formal announcement by email, and so there won't be anything more formal here, except for to acknowledge the fact that these seminars are a lot of fun, and they're a great way to connect with people and keep up on recent results. And we're very lucky that people like Federico are prepared to give a talk by Zoom. There's lots of things that are nice about Zoom. We're all in different places and going to enjoy this talk and the interaction. And then the downside is to give a talk into your screen. So let's remember that and come up with some good discussion points and participate when it gets to that point later in the talk. Just to ask people to mute themselves, but encourage you to interrupt with points of clarification or minor questions before we get to the end. There's usually plenty of time to have a real nice discussion and question and answer period. So, with nothing else, I'll thank Federico again and turn things over to him.
Thank you, Chris. Thank you for having me here. So today I'm going to present the work I've been doing in collaboration with Robert Vieska and Dimitri Garagash. Actually, I started this project a couple of years ago when I joined Tufts University as a postdoctoral researcher, but I'm still working on it here at Northwestern University. So part of the results that I'm going to show today is currently under review in the proceeding of the Royal Society A. Some other results haven't been published yet, but we have a manuscript under preparation. So today I'm gonna be talking about elasto-frictional length scales and their role in governing sleep dynamics on right-hand state fault. Let me start with some basic concept of elasto-frictional coupling. So imagine that we have a planar fault. This can be finite or infinite, which is embedded in an unbounded homogeneous isotropic and linear elastic material. And so this is actually the configuration that I'm going to be focusing today. And let's also suppose that the fault is undergoing some sleep. So we know that from Buchner's theorem, the shear stress on the fault plane can be decomposed in three different components. So the first one is given by the applied stress on the medium. The second one is the change of shear stress due to a non-uniform distribution of sleep or sleep rate. Actually, in the elastodynamic, this term here depends on the history of sleep or sleep rate. And finally, we have also the radiation damping term, which was introduced by Jim Rice in 1993, which actually represent the energy outflow as seismic waves. It's an approximate term for the elastodynamic shear stress change because it doesn't consider the wave propagation effect, right? And so this term is also proportional to the sleep rate, so it becomes significant when the sleep rate tends to blow up. Then let's also suppose that the material surrounding the fault is brittle, has a brittle rheology. So the fault strength is governed by fault friction. And in particular, here we're going to focus on right-hand state dependent friction. And so the fault strength, tau S, is given by the friction coefficient times the effective normal stress. And the friction coefficient is given by the standard formulation of right-hand state dependent friction, which was introduced by Jim Dietrich and then in Ruina in the late 70s. So here the state variable is a given function of the sleep rate and theta, which is the state variable. We're gonna see the AG law, but also the sleep law and some intermediate state evolution law later in this presentation. So as I said, the fault is undergoing some sleep. So on the sleeping patch, the shear stress must be equal to the strength of the fault, right? Now let's rewrite the equation that I just wrote in the quasi-dynamic approximation. So we have the strength of the fault on the left-hand side, and on the right-hand side we have tau load. So this is a linear operator, is a non-local linear operator that acts on the gradient of the sleep distribution on the fault. And finally, we have this radiation damping term here proportional to the sleep rate, as I said before. So now let's normalize this equation by introducing some characteristic scales. And so here I scale the shear stress by B times sigma prime n, the sleep rate by the creeping rate V plate, which is assumed to be equal to the reference velocity V star. theta by d sub c divided by v plate, and the slip by d sub c, and all the spatial coordinate by the half length of the fault. And so if we introduce these characteristic scales and we take also the time derivative and we neglect the variation of the load, the tau load in time, then we can obtain this equation here, this normalized equation here, where we can identify three different governing parameters. So one is A over B, which is the ratio between the phenomenological parameters of rate and state dependent friction. The second one is L divided by, or LB divided by L. So LB is this elasto-frictional length scale that emerged from the coupling between elastic deformation and fault friction. In fact, this is given by the mu prime, which is an effective shear modulus of the medium, which depends on the mode of the deformation, and times d sub c divided by b times sigma prime n. And finally, we have this dimensionless group here, which essentially modulates this radiation damping effect. And so if you're interested in understanding how and when an instability develops on a fault, then we would be interested in understanding how V dot diverge in time, right? So this actually form a system of ODs. And so we can, just by looking at this system of ODs, we can immediately understand that for a given value of A over B and a given value of this ratio here, an instability may develop or not, depending on the ratio of L or divided by LB, right? And so if an instability eventually would develop, then we would have the fault length, actually the critical fault length is proportional to this elasto-frictional length scale LB, right? However, this is not the LB emerge because of the introduction of this characteristic scale. However, there is not a unique normalization, right? We can introduce different characteristic scales, which would result in a different elasto-frictional length scale. However, LB is not a bad choice for a characteristic scale for the nucleation length of a slip instability. In fact, we know that from a linear stability analysis in a springs block model, there exists a critical spring stiffness below which, if you introduce some small perturbation to the steady state sliding, this perturbation develop and evolve to a slip instability. And so this critical stiffness was introduced by Andy Rina in 1993 and is given by B minus A times sigma prime n divided by D sub C, which can be rewritten as B sigma prime n divided by D sub C times 1 minus A over B. And so here I call it this ratio KB, which is actually a characteristic stiffness for the critical value, right? So if we divide the kappa critical by this stiffness kappa B, we would obtain 1 minus over B, which is of the order 1, right? And so this is actually a characteristic stiffness for kappa critical. And so imagine that we have we have a finite fault of half length L. So a stiffness can be approximately given by mu prime divided by the total length of the fault. So this is just an approximate value. We're going to see later in this presentation a more accurate value of a stiffness for a finite fault, for a continuum finite fault. But if we equate this value of the stiffness with the kappa critical, then we would obtain the critical length scaled actually by the characteristic length LB. So essentially, LB is a good characteristic scale for the nucleation length. So we've seen that when we couple elastic deformation and friction, then there are these elasto-frictional length scales that emerge, and these actually are known to impact the earthquake nucleation process. So we know that some theoretical arguments indicate that earthquake starts slow with a quasi-static preparatory phase. So here, this is what is depicted here in the figure on the right. So we have time in the y-axis and space in the x-axis. And so we see that there is a crack-like propagation with well-defined leading edges that is propagating, expanding up to a critical value that I call it L critical nonlinear, after which a dynamic rupture takes place and inertia kicks off. So in general, this critical length is proportional to, as I said, to an elasto-frictional length scale. And the question whether this critical length is universal is a matter of subject of many studies, right? So we're going to answer to this question later in this presentation, when it can be considered to be characteristic and when it's not. But provided that this is actually what happens for a real earthquake nucleation, then what these tell us is that a fault that is not sufficiently long would never host a dynamic instability, right? Furthermore, the presence of a characteristic length scale for dynamic rupture nucleation makes this earthquake nucleation problem not self-similar, right? Think about a fluid diffusion problem. A fluid diffusion problem is self-similar because there is no time or length scale involved in the problem, so the solution is invariant to any stretching. However, here, because we have this characteristic, we have this length scale, right? So the nucleation process is not similar. And this is actually lies in contrast with some earthquake source model. For instance, the one of a circular track that is expanding at rupture speed and a constant stress drop. This was actually the model proposed by Kostrov in 1964. So in this model, so the rupture area scale quadratically with time, the average slip linearly with time. So the seismic moment to the is to the time to the power of 3. So if you take the time derivative, the seismic moment rate would scale quadratically with time. And we know in seismology that the displacement is proportional to the seismic moment rate. So which means that if we take the time derivative of this expression here, we would expect that the velocity at a given point would increase linearly in time. However, this is not what is observed, at least for this particular case here. So here I'm reporting the broadband velocity recorded by a seismogram during the magnitude 6.1 Joshua Tree earthquake in California. So this is actually the same velocity curve, but so this upper curve here is magnified 12 times. And so what we can observe is that so time has been normalized such that time 0 is the arrival of the P wave. And what we can observe is that after the arrival of the P wave, there is an increase of slip velocity up to let's say in this case for 0.12 seconds, and then before actually the real earthquake take place, and followed by a quadratic growth of the moment rate. So there seems to be a weak motion preceding a strong motion. And this seems to be also consistent across several earthquakes. So this is a table compiled still by Earthworks and De Rosa in 1995. So there are 30 earthquakes with magnitude like from 8.1 to 2.6. And here in this red column, we can see this is the duration of this preparatory phase, which can be 5 seconds, order of a few seconds, but also very, very quite small, like 0.008 second. And this is the percentage of the seismic moment released during this aseismic or this quasi-static motion. So it seems to be consistent. And this is also what is observed in laboratory experiments of earthquakes. So this is a nice experiments done by Greg McCluskey and his group in 2019. So the apparatus is pretty unique. So they have 3 meters long samples that is sheared, that is loaded through the usage of 54 hydraulic cylinders, and there are a sensor all along the fault that can measure the spatial temporal evolution of slip. And so so they run an experiment, and this is here I'm showing the results. So a vertical axis is slip, and the x-axis is the distance along the strike. And what we can observe is that there is the rupture initiation is roughly 0.5 meter from the left edge of the sample. And then there is so each slip profile is drawn every 200 microseconds. So if the contours are very, very close to each other, it means that the propagation is low, is quasi-static. Whereas if the two contours are quite far from each other, then it means that the rupture is very fast, right? And so the rupture initiated at roughly at 0.5 meters, and then propagated bilaterally. So it reaches the end of the sample on the left-hand side, and then it propagates roughly for 1 meter on the right-hand side up to a critical value, after which there was a dynamic rupture. So there seems to be also here a quasi-static nucleation phase before the dynamic rupture nucleation. This is also another set of experiments done by Latour et al. In 2013. Here they use a polycarbonate. So they loaded the sample through the using manual pump, and they use photoelasticity to track the rupture, nucleation, and propagation. And they actually observe a very similar behavior, right? So here is a time versus the length of the fault, and each plot is as a different normal stress, applied normal stress. And we can observe is this quasi-static nucleation phase up to this a critical value, after which there is a very fast dynamic rupture. And of course, as I said before, the nucleation length is roughly proportional to LB. So if we increase the normal stress on the fault, we would decrease LB, which means that you would decrease also the nucleation length. And this is what is observed also in this experiment. And so they also develop a theoretical model, and they get a good match between observation and this theoretical derivation. However, so in rate and state friction, there is also another critical dimension that matters. So this critical dimension, this critical length was actually, this is what is known H star in the literature. This was introduced by Jim Rice in 1993, actually to explain the apparent emergence of sleep complexity in discrete numerical simulation. And so, so to develop this critical dimension, Jim consider an infinite fault that is dividing two unbounded elastic half spaces. And we know that the stiffness, if you apply monochromatic perturbation, the stiffness is actually given by 1/pi times the effective shear modulus divided by lambda, so the perturbation wavelength. And so if we consider the perturbation wavelength is arbitrary, right, it can be considered. So if you assume a very sufficiently or infinite long cell, then the stiffness for this infinitely long cell is actually given in an approximate way as 2 times mu prime divided by pi times h. And then if we equate this stiffness, this approximate stiffness, with the critical stiffness of the spring slider block model that I showed before, then we can obtain h star, which is given by 2 divided by pi times lb divided by 1 minus a over b. So now that this prefactor is 2/pi, and we're going to come back to that later in the presentation. So this h star can be considered as a nucleation size for sleep instability. And so Jim Rice, actually, in his very famous JGR paper in 1983, showed that if h star is under-resolved, then a single cell actually would fail independently of its neighbor. So we don't have a really truly continuum representation. So in numerical models, we have to resolve this critical, this length scale with sufficiently large amount of elements. And so here, in fact, you can see that, for instance, in this simulation here, H is, so we have 4 elements that is resolving H star, and we get a smooth profile of accumulation of sleep along the fault. Whereas if we don't resolve this critical length, then we get really awkward results, unphysical results. And so, but the H star has been used to explain the generation of slow sleep events. So this is for instance, an example of a model that was done by Leo and Rice in 2007 and 2009. So they look at this at the Cascadia subduction zone, where they have this the oceanic plate that is subducting beneath the continental plate. And so this is the evolution of the effective normal stress along the subduction zone, where we have a larger effective normal stress near the trench of the subduction zone, and then this effective normal stress becomes near the lithostatic one, and then we have the creep in the down deep portion of the subduction zone. And so from this realistic model, they made a simplified model where we have here the trench is locked, so there is no sleep. Then there is a rate weakening patch, followed by a rate strengthening region, and then a creep in the down deep portion. And so they run elastodynamic simulation, and they obtain this response phase diagram. So here in the y-axis is the d sub c of rate and state friction, and the x-axis is the w, so the total length of this rate weakening patch, scaled by h star. And what they observe is that depending on the ratio of this w divided by h star, we may expect a decay of oscillation, periodic so for instance, if W divided by H star is below 2.16, then if you apply perturbation to the fault, then this perturbation, this creep actually die out, and we would achieve a steady state sliding. Not that so W is the total length of the rate weakening patch, right? Which means that if you consider the half length of this patch, this would tell us that when the half length of the patch is approximately given by H star, then we have this transition between a decay of oscillation and the simple periodic. So this H star actually is important, is an important length scale. And so then if you increase W by H star, we get this perfectly like limit cycle, perfectly periodic oscillation of slip rate. In this case here, we have a complex, they observe complex periodic and aperiodic oscillation. And finally, if the rate weakening patch is sufficiently larger than H star, then you expect the seismic events, right? But these are actually simulation, right? This is the results of a numerical simulation. A similar model was also used by Rubin in 2008. So it's actually very, very similar. So there is a locked, so this is the slip is pin at this point here. We have a rate weakening patch followed by a rate strengthening region and then V plate. And what Rubin observed is actually very similar response. So here, there are the results of the log of the V plate, and the red curve is the slip, the accumulation of slip in time. And all the different plots are characterized by different ratio of W divided by H star. And so we can see that depending on this ratio, we observe like simple periodic behavior or complex behavior or periodic instability, right? And so what do we know so far? So far we know that there is this H star that is the nucleation length for slip instability. So it has its origin in a linear stability analysis considering an infinitely long rate and state fault, right? With homogeneous frictional and loading condition. And we know that if the half length of the fault is smaller than this H star, then any instability can never develop. And if on the contrary, if the fault length is larger than H star, then an instability may actually develop. However, this is not sufficient to ensure that such an instability actually nucleate a dynamic rupture. And so there is another length scale that I mentioned before, that to be LC nonlinear, which is of course larger than H star, where if the fault is larger than this LC nonlinear, then we would expect a dynamic instability. And so, of course, this takes into account the nonlinear coupling on friction and elasticity. So the state evolution does matter in this critical length in the nonlinear regime. So in the AG law, we know that when A over B tends to be 1, we have a crack-like type of nucleation. And this critical length is given by LB divided by pi times 1 minus A over B squared. So this is known in the literature as L infinity. Whereas when A over B tends to 0, then the healing is not important. So the blow up occurs on a fault patch of a fixed length. And this critical length is given by 1.3774 times LB, and is also known as L mu in the literature. On rate and state fault, with the slip law, we have a bit different, more complex enucleation procedure, where we have a kind of a pulse-like nucleation. And Rob actually showed that this critical nonlinear can be vanishingly small. However, also this critical length in the nonlinear regime is obtaining assuming uniform frictional properties and loading condition. And so when we have more realistic configuration, where we have, for instance, a rate weakening followed by rate strengthening, so all the studies mainly resolve to numerics. And so here is a nice study of Camilla Catania in 2019, where she looked at the emergence of complexity in isolated faults governed by the AG law, state evolution law. And so this is on the right-hand side, you see the main result of the paper. So y-axis is A over B, and the x-axis is this is W divided by L infinity, where W is the extent of this rate weakening portion of the fault. And what you can observe is that depending on this ratio of W divided by L infinity, there are some, so either we expect a simple one earthquake per cycle, or if this length is sufficiently large, then we get some partial rupture, so some complexity that emerge. A similar study was done by Nie and Barbeau in 2021. Essentially, in the y-axis is 1 minus A over B instead of over B than before, and in x-axis is W times 1 minus A over B divided by LB, which is essentially W divided by H star on the except that there is a prefactor missing, right, which is 2 over pi. And so depending on this Dietrich-Ruina number RU, then we expect creep, a seismic sleep, or earthquakes. But all these phase diagrams are actually obtained through numerical simulation. So the question that we want to address in this contribution is, can we precisely quantify the stiffness of a continuous finite fault with homogeneous and eventually heterogeneous frictional properties and loading condition? The second question that I want to address is, can we accurately determine the critical length for the nucleation of dynamic slip over the entire range of A over B 0 and 1, assuming homogeneous and heterogeneous distribution of frictional properties and loading condition? And finally, what happens when the frictional state evolution law deviates even slightly from the AG law? And so we want to address to this question, but without relying on numerical simulation at first end. So numerical simulation will only be used to verify our theoretical prediction. So let me start again from the linear stability analysis of the spring block model. We've seen before that, okay, here we are doing linear stability analysis, so we're looking at the linear regime, so slip law or aging law doesn't matter, right? Because they both share a common linearization about steady state sliding. So if you introduce some tiny perturbation in this form here, it can be shown that there is this critical stiffness that I was mentioning before that is given by sigma prime. This is sigma n times b minus a divided by d sub c. So if kappa is larger than kappa critical, then this perturbation die out in time. If kappa is equal to kappa critical, we have a periodic, perfectly periodic oscillation. And if kappa is smaller than kappa critical, this perturbation tends to increase, to diverge in time. So the question is that what is the stiffness of a finite fault? So in a finite continuum faults, there exists infinite discrete number of stiffnesses. So actually it can be shown that the stiffnesses are given by eta I times mu prime divided by L being the half length of the fault. And so Ni, I can range from 1 to infinity, but the first values of Ni is 0.579, the second one is 1.3774, and so on. And so since we are interested in the smallest stiffness, right, that would give the smallest critical value, then we pick the first value 0.579. So we can write it. So and then we can equate this kappa to the critical value of the spring block model. So we would and then this would we obtain 0.579 times LB divided by 1 minus over B. So note that the prefactor 0.579 is actually quite different than the prefactor associated with the H star, because the one that I was showing before, the H star was 2 divided by pi, which is roughly 0.637. Here is actually smaller, right? So now that this solution can actually be retrieved by solving a linear stability analysis directly on a continuum fault model. So we can do that. And so here is actually how the complex, so how the eigenvalues would look like at the first of bifurcation in the complex plane for a given value of A over B. And so you can see here the first of bifurcation when the eigenvalue cross the imaginary axis, which is this vertical axis here. So in our paper that is currently under review, we also calculated the stiffness for different continuum configurations. So the first one, we look at the infinite fault, which is embedded in an unbounded medium. And if you apply this monochromatic perturbation, then we would easily, well, one can easily show that the stiffness is the stiffness scaled by the characteristic stiffness is given by pi. But also this infinite fold can also be close to the free surface, so the prefactor actually would change, and actually the elastic operator would actually change because we are moving from a non-local operator to a local one. And also we also calculate the stiffness for a finite fault near a free surface, and also for a circular fault embedded in a infinite medium. And of course, these are the smallest value because there are many, as I said, many values. So we're always interested in the smallest value. Now, if we plot the solution that I showed before, so this is L scaled by LB versus 1 minus over B. So we have a straight line, right? So if we are in this part of the plot here, we're in the linearly stable regime. So the fold length is actually smaller than the critical value, which means that even if we apply perturbation to the motion, then this perturbation die out, and we would achieve a steady creep. So if we are in this range, in this part of the diagram here, then we are in the linearly unstable regime. So this perturbation tends to increase. So the question is, do we expect an instability or do we expect a dynamic rupture or not? The question is, well, it depends, as I said before, to another critical dimension that accounts for the nonlinearity. So let me first do a brief excursion on a sleep instability and on a sleep weakening fault. So we're moving from latent state to sleep weakening for just one slide, 5 minutes. So here I'm reporting the equilibrium in a quasi-static approximation for a sleep weakening fault. We have again the elastic operator, which is given by Taube-Grand, which is the applied loading scaled by Fp minus Fr, where Fp is the peak value of a friction coefficient and Fr is the residual value of friction coefficient. And so if we take the time derivative and we neglect this sigma prime dot and Taube-Grand dot, because these are actually smaller compared to the diverging sleep rate, then we would obtain this eigenvalue problem here, where L star is this elasto-frictional M scale, which resemble the LB of the latent state, but right, so D sub C is actually replaced by delta sub C, which is the critical value after which the friction becomes constant. And then on the denominator, we have Fp minus Fr instead of the B of the latent state friction. And so this is an eigenvalue problem. It's a well-known eigenvalue problem that we can solve here, use Gauss-Chebyshev quadrature to solve this eigenvalue problem. And we would, if we solve it, we would obtain this critical value nonlinear regime for a sleep weakening fault. And so we know that the first eigenvalue is actually given by 0.579, and these are actually the the first 4 eigenvalues. These are the eigenmodes. And so we can see that, for instance, the first eigenmode is symmetric, the second eigenmode is antisymmetric, and so on. And so these results are very well known, and these were obtained by Venetian Rice in 2003. But also a similar study was also done by Campillo and Ionesco in 1997. So this is a universal nucleation length for dynamic instability, dynamic rupture instability on a sleep weakening fault. So now let me go back to the latent state dependent friction. So the purpose of that excursus is that we will see there are some similarities between latent state friction and sleep weakening friction. So now, as I said, we're looking at the nonlinear regime, so the state evolution does matter. So if we focus on the aging law, Rob actually showed that scaling consideration suggests that sleep rate blows up in a subsimilar fashion. So we can write it as d sub c divided by Tf, where Tf is the time away from instability, times W, which is a subsimilar blow-up profile. And so if we plug these ansatz in the evolution equation for V and theta, then the problem of determining the support for this dynamic instability actually reduced to the problem of determining the fixed point of a dynamical system. And so when Rob did that back in 2016, he realized that he ended up with this equation here, which resembled very much the sleep weakening problem that I just showed in the previous slide, right? It's mathematically very similar. So if you apply actually this mapping, we can actually map this nucleation problem for a rate and state fault to the nucleation problem of a sleep weakening fault, right? And so we can readily solve this problem using Gauss-Chebyshev quadrature rule. Actually, this is a free boundary problem because what is unknown here is the support for the dynamic instability. So is L critical nonlinear as well as the W, which is the self-similar profile, right? So it's a free boundary problem. But we can solve it using Gauss-Chebyshev. So, and here I'm reporting the solution as a function of A over B. So here is this critical length in the nonlinear regime versus 1 minus A over B. And so what we can observe is that when A over B tends to 1, so 1 minus A over B tends to 0, then this critical value, we retrieve the solution that I was showing before, which is given by LB divided by pi times 1 minus A over B to the power over 2. So in this log-log plot, we have a linear curve that is with a slope of -2. And then as we decrease A over B, then the solution actually, there is a bifurcation of solution. So there are two branches. One is this one, and the other one is this one. So to capture these two branches, what we change is the behavior of the sleep gradient near the rupture tip. So in what we call non-singular sleep gradient, we solve it actually because there is a cohesive zone length. There is a cohesive zone near the rupture tip, so the sleep gradient is non-singular, and so we obtain the solution of that I was mentioning, which is L critical nonlinear is 1.3774 times LB. However, if we pin the sleep near the rupture tip, we obtain another branch, which is given by roughly given by 0.579 times 1 minus A over B to the power of -4 divided by 3. So which tell us that the smallest possible nucleation length for a dynamic rupture can be reached when A over B tends to 0 and is approximately given by 0.579 times 1 minus A over B to the power of minus, no, it's actually 0.579. That's it. All right, so if we put together these two critical value in the linear and the nonlinear regime, then we would obtain this phase diagram here, which is valid for a homogeneous scenario with aging law state evolution. And so we have these three different regions. This is linearly stable. Here we are linearly unstable, but not linearly stable, where we would expect a seismic transients. And then in this region here, we are not linearly stable, so we would expect seismic cycle. So now to check the prediction of our analytical boundaries, so we run some elastodynamic simulation. So I developed a spectral boundary integral equation method solver to simulate these sequences of earthquake and seismic slip-on faults. I'm not gonna go into the details, but the key feature of this solver is that unlike the traditional spectral boundary integral equation method-based solver, here we avoid the replication of the rupture event in space by using the amendment proposed by Ciardo and Rice in 1997. And so we also benchmark, we verify our solver against the SCEC BP1FD exercise for modeling of SEAS. And these are my results. So this is depth and cumulative sleep, and this is the comparison with all the solutions that are actually reported in the online platform of SCEC. And so our results, so this is the sleep rate in time at a different depth, and we can see that our results are in very good agreement with those of Jengol Yang, who use the bicycle code. So now we test, so we fix A over B to be 0.9, and then we check this stability, these boundaries. So for this case here, we would expect we are in the linearly stable regime, and in fact, so we start above steady state, so we give a kick to the fault, and this is the maximum slip velocity in time, and we can see that upon some oscillation, this perturbation die out in time and steady creep is achieved. in this, if we cross this linear stability boundary, then we achieve a limit cycle, so perfect periodic oscillation of sleep rate. And then if we get closer to the other stability boundary, then the maximum sleep rate increases, but still below the dynamic threshold value for this specific simulation here, which is 0.18 meter per second. And then if we cross this boundary, then we obtain seismic events, periodic events with seismic sleep. Also, I want to show that okay, as expected, when the fault is very large and is much larger than this critical value in the nonlinear regime, then we would expect also the emergence of sleep complexity. And so in this case, I fix the total length of the half length of the fault to be scaled by LB to be 10 times larger than the critical value in nonlinear regime, roughly. And in fact, so this is I'm plotting the time step versus versus the spatial coordinate, and we can see there are some partial rupture that are nucleating, and we don't have actually the nucleation at the middle of the fault because the fault is loaded by creep at its extremities. Now we can also look at a more interesting scenario, more heterogeneous scenario, where we have a rate weakening patch that is sandwiched between two rate strengthening region. And so thanks to the method of image for mode 3 type of deformation, this scenario is actually equivalent to this type of scenario here, which was the same scenario of Camilla Catania work. Where we have this strike slip fault with the rate weakening followed by rate strengthening, and the fault is loaded by creep in the down deep portion of the fault. And so we can exactly do the same thing. We can obtain a W. So now we can fix the total length of the fault and solve for the critical value in the linear and in the nonlinear regime of this asperity, which is this region of rate weakening frictional properties. And then we would obtain this phase diagram here, where we have again these three different regions. So I'm not going to show. We also check that the numerical through numerical simulation that these boundaries are actually accurate. But what is interesting is how does the W critical in the linear regime vary when it's comparable or much smaller than the total length of the fault? And so here I'm showing on y-axis is this critical value scaled by LC in the homogeneous scenario, and the x-axis is W divided by L. So when W divided by L is roughly 1, so we are in this configuration here, where this rate strengthening region is very small, very, very small compared to the rate weakening region, right? And so we would expect that the rate strengthening effect is actually negligible. And in fact, we see that this critical value actually starts to this value here, which is given by L critical homogeneous, which is 0.579 times LB divided by 1 minus A over B being in the rate weakening portion of the fault. And as we move to the other side of the plot, we are in the opposite scenario where we have this rate weakening region that is very small and the rate strengthening region that is much larger. And so in this, and you can see that there is a nonlinear evolution of this critical length, and you reach kind of a plateau when this duration reduces to 0. And in fact, it can be shown that this plateau is given by the scenario of an infinite fault. So essentially, there is this critical value doesn't feel the effect of the finiteness of the fault. And so we were able to solve also this problem of an infinite fault using a spectral method following Weidman 1997 work. And so you can see that the results actually converge to this dash red line pretty well. But also we can fix the value of the A over B in the rate weakening portion of the fault, and we vary the A over B in the rate strengthening of the fault. And so, as we would expect, right? So if the rate strengthening if A over B in the rate strengthening of the portion of the fault increases a lot, then you kind of effectively lock the fault, right? And so we would expect that this critical value actually reaches a plateau, and the plateau being the critical value in the homogeneous scenario for a fault of total length of 2W, right? So essentially, the rate strengthening region of surrounding the fault asperity can effectively lock it when A over B is sufficiently large. And this is not very surprising, right? But it's good to confirm it. So now the question is, so far I focused, all the results were focused on aging law type of state evolution. So what happens when the frictional state evolution law deviates from aging law? Does this critical nucleation length for dynamic sleep always have a characteristic value? So to answer to this question, we perform a nonlinear stability analysis, but in this case, using not a continuous model, but a discrete model of a spring block model. So here we neglected inertia for simplicity, and we use a state evolution law that is an intermediate state evolution law that bridges aging to sleep law via dimensionless parameter epsilon. So when epsilon is equal to 1, we retrieve the sleep law, and when epsilon, in the limit of epsilon that tends to 0, we retrieve the sleep law. And so if we were able to solve analytically for some set of dimensionless parameter this problem. So let me just show how a trajectory in the phase plane would look like. So we have so in the y-axis is the shear stress, in the x-axis is the sleep rate. So we may obtain an open trajectory or a closed trajectory. So initially, we assume that the block is sliding a steady state. So here phi is 0 because v is equal to v star and tau is equal to t star. So the initial point is here. So if we apply a rapid perturbation, a sudden perturbation, then the state is constant. So we will jump at 45 degrees on this diagram. And depending on the jump, we may this point may end up on a closed orbit or a open orbit. So closed orbit is stable, and the open in the orbit is unstable. So let me show with a very simple animation. So if in this case we apply a perturbation, the points jump on an unstable trajectory, and we get unstable sleep. And then if the perturbation is not sufficiently large, then we will see that we would end up in this closed trajectory, and we get this kind of a stick sleep behavior, stable periodic increase and decrease of sleep rate. And so we were able to solve this problem analytically when kappa is equal to kappa critical being the critical stiffness of Ruina 1983. And so we were able to solve this problem depending on for different value of epsilon, right? Epsilon ranging from 0 to 1. And so when epsilon tends to 0, then we retrieve the results of Gu et al. 1984. And when epsilon is equal to 1, we retrieve the results of Ranging and Rice in 1998. These are sanity checks, right? And then for intermediate state evolution law, so what we can observe is that as the state deviates from the Engel law, we have open trajectory and closed trajectory. So these open trajectory and closed trajectory are actually separated by this critical trajectory, which is this red trajectory here. And so depending on the jump, on the perturbation you apply, so if the perturbation is larger than this critical value, then we would expect unstable sleep. On the contrary, if the perturbation is not sufficiently large, then we would end up in this closed trajectory. And so because all these trajectories are analytical, we were able to obtain the critical velocity jump as a function of the epsilon parameter. And so what we can observe is that this critical velocity jump actually diverge as epsilon tends to the aging law. Okay, let me put in a different way. So if epsilon is equal to 1, then this critical, so you never get any instability because this critical velocity jump will actually be infinity, right? So regardless of the perturbation that you apply to the system will always be stable. But as this frictional state deviates even slightly from the aging law, so there exists a critical perturbation to the system that can bring the system to an instability, right? And so there is this loading-dependent instability, right? As the state deviates from the aging law. In this case of kappa is equal to kappa critical. So when kappa is different than kappa critical, we were not able to solve the problem analytically. However, we were able to solve it numerically. And so this is a summary of the results. So this is the y-axis, the loading rate jump. So it's the perturbation that we apply to the system. And in the x-axis is kappa scaled by the critical value. So, and all the curve corresponds to different value of the epsilon. So this pink curve is epsilon is equal to 1. And then when epsilon tends to 0, we have this brown curve here. And so let's focus on, for instance, on this curve of 0.225. So if you apply a supercritical perturbation, then we would expect an instability, right? If a perturbation is near critical or subcritical, that we would not expect an instability. So we can observe that when L, because kappa is inversely proportional to the length of the fault, so when L is smaller than L critical, then depending on the perturbation that you apply to the system, then you may actually trigger an instability, right? So we have this loading rate dependent nucleation. And this is actually consistent with also results obtained on a continuum fault with an intermediate state evolution law by Robert Wieska in 2023. Actually, Rob showed that also when the frictional state deviates from the AG law, the state evolution, the slip rate diverges in a self-similar fashion. But the distances here are scaled down by a factor of epsilon, which means that when epsilon in the slippery law, when epsilon tends to 0, then we can actually get theoretically a point-wise divergence of slip rate. And what he did also very cool is that he performed a linear stability analysis of a non-linear blow-up solution. So for instance, let's focus on this plot here on the left. So this is the complex plane, and this is how the eigenvalues move in this complex plane. So here, if he fix epsilon to 1, which means he focuses on the AG law, and he changes the A over B. And so we can observe that when you increase A over B, the eigenvalues move in this complex plane, and they cross this vertical axis here. So once they cross this vertical axis here, the solution is unstable, or if not, is stable. So if a solution is stable, it means that the instability is actually attracted in a self-similar fashion. If a solution is unstable, then it's not the case, right? And so these are actually the results that he reported. So there exists a critical value of A over B for which the solution becomes unstable. So the blow up would not be in a self-similar fashion. But these were results obtained in 2016, I think. But in 2023, what he did is that he said, okay, let me fix A over B to 0.65. And in A over B 0.65 is stable, which means that the slip rate would actually diverge in a self-similar fashion if the aging law is considered. And then let me change the epsilon and let me decrease this epsilon. So when epsilon tends to 0, so you can see that the eigenvalues actually move in this complex plane and reaches so actually the imaginary part of the eigenvalues actually would disappear. And what you can observe is that, again, if you focus on this trajectory here, there is a critical value of epsilon after which the solution becomes unstable or below which the solution is stable. And you run quasi-dynamic numerical simulation. For instance, here is A over B 0.65. So when epsilon is equal to 1, we are in this stable branch, which means that, in fact, you can observe in this black curve that the slip rate blows up is attracted to this self-similar blow-up solution. But if for a smaller value epsilon 2 is really very small, like 0.068, so he crossed the stability boundary, and in fact, this solution is not attracted anymore to the self-similar blow-up solution, but actually there is a slip pulse nucleation. And so finally, let me get to the conclusion. I want to summarize all the results by mentioning there are two relevant length scales that govern the slip instability on right-hand state faults. The first one is valid in the linear regime and determine whether a slip instability can develop or not. However, I want to stress the fact that this critical in the linear regime is not the nucleation length for dynamic slip nucleation, right? So we have also precisely quantified this critical dimension for finite faults and for homogeneous and heterogeneous frictional properties. And also we also have quantified this critical length in the nonlinear regime. So this depends on the nonlinear elasto-frictional coupling, and therefore on the state evolution law, the particular state evolution law considered. So under the AG law, this nonlinear length is well defined, so there is a critical value after which we would expect dynamic stability. However, when the frictional state deviates even slightly from the energy law, this nucleation process becomes loading dependent, and therefore there is not a universal or characteristic value for this critical length. Thank you for your attention, and I would be happy to answer any question.
Thank you very much, Federico. That was really a fabulous talk. I will invite people to unmute. Join me in thanking Federico. A really great talk. A lot of things to think about. So,
Thanks.
okay.